to a 5x5 filter. So it becomes a little more involved, but the concept, you already have it. So anyway, somebody had a question.
Yeah. For heat elevation filter, we add 4 pixels and subtraction the center.
4 times the center.
Yeah, what we have like overflow because we are adding 4 different pixels.
Yeah, then typically what we do in these case of filters, then we go 0 to 255, and if it drops below 0, we set it to 0. If it exceeds 255, we set it to 255. Okay, so anyway, so hopefully, like I said, now you have a good overview of the filters and how do we come up with a particular kernel. Once again, what we covered, averaging Gaussian, difference of Gaussian, binomial, first order derivative, component filter, gradient filter, Laplacian filter, and lastly, the Laplacian of Gaussian is often used also.
So are the derivative filters, are they the high pass filters?
No, these are more like, sorry, they are high pass filters, yes, because they enhance the edges. So anytime because edge is like a sharp transition, which has a lot of high frequencies. So if you're enhancing the high frequencies, so it is more than a high pass, not only it's passing those high frequencies, it's further increasing their amplitude. So, that's the purpose of the derivative filters. Okay. A simple high pass will just pass the high frequencies, but will not enhance them. Okay, now let me show you one example of where all these concepts are used. Okay, and we'll take a look at a practical example. So one of the Okay, by the way, in the second assignment that I put on the website, I asked you to give me kernels, by doing the derivations. So essentially, all I'm asking is redo the same thing I covered in the class. But the idea is, as you go through it yourself, write it down neatly. It will strengthen, your own knowledge and will stay with you for a longer period of time. And then the second part of the second assignment is you will actually program these filters. And I gave a very poor starting code on purpose so that you try to improve it. So my suggestion would be for the second assignment, let me show it to you first. Then we'll talk about it. Okay, so if you go to the CPEG585 website, like I said, second assignment, let me just briefly talk about it. Okay, so let's take a look at the first problem, 8 parts to it. Derive the kernels from the following, right? So again, same thing as we discussed. When you do the difference of Gaussians, sigma 1 you'll pick to be 0.5, sigma 2 to be 2.5. Anyway.
Can you try lowering the volume?
Lowering the volume?
Yeah.
Okay, then the second part of the code is write the code for testing the above kernels. The starting code I provided in C#. Okay. Now some of you already are pretty decent in C#. Some of you are new to C#. I'll have one of our PhD students help out. So if you're having any problem with the understanding the C# code and making progress, especially first month or so, I'll put the information about the PhD student. Feel free to contact the PhD student, take your code, and she'll help you. Anyway, for the code that I gave you, like I said, it's poorly written code, so that you can easily understand it. But what I'd like you to do is, when you do this assignment, hey, I'll have you create a menu, and it will say filter kernel as an example. Okay, so once you click on this filter kernel menu, then it should give you a form. And in this form, what you can do is you can put 9 text boxes. Okay, so the idea is somebody can enter, for example, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, -4 over there. Okay, so somebody enters this as a kernel and they submit. So this is like a button. Okay, so then your form will receive this kernel 0, 1, 0. It will store it in a 2-dimensional array. And then it will loop through, apply this to the first part, then keep moving the kernel, and then finally you'll display the image. So this way, you don't have to write code for all these separate kernels. There's a single code, but through the UI you can enter any kernel. And in the assignment, you will just enter the identity kernel, display the image, and then put it in a Word document as you submit it. Same thing for all of these. So from coding point of view, the only thing you need is be able to collect the kernel through a UI, and then try to write the code a little bit better than I have, so that it's cleaner and it does the job. There are some programs available on the internet that will do this kind of thing. I mean, if you copied and submitted, I won't care. But see, you want to learn and get better at programming. So do it yourself. Don't try to take the shortcut. Okay. Anyway, so that was the second assignment. So now let me cover one topic where we apply some of these concepts in a practical manner. So one of the filters, which is very popular, is called canny edge detection. So for detecting edges, this is considered one of the best filters. Okay. The code for it is already available in every popular computer vision library. Okay, so I won't have you program this from scratch, but at least I'll show you the background behind this algorithm so that when you use it from a library, you can easily understand what are the parameters that we control and how does this algorithm work, right? So we'll be using, for a lot of our computer vision work, a library called OpenCV library. Okay, this was created by Intel. Okay, originally it's written in C++, okay, but it has wrapper for Python and a wrapper for C#. C#. Okay, the wrapper for C# is called EMGUCB. And it's very easy to install. I'll show you, if you wanted to use OpenCV, gradually you will be using OpenCV as we do something more interesting, more sophisticated. Okay, and then later on we'll also, because some of our computer vision work in the second part of the course will be related to deep learning. So then we'll be using Python. So then gradually we'll switch to Python. But anyway, in the beginning, at least as we are covering the fundamentals, this is what I'll be showing you with before I switch to Python. So let me quickly show you how do we install EMGUCB in our project. Okay, so what you do is you launch Visual Studio. Okay, once you launch Visual Studio, you'll create a new project. For example, file, new project. Okay, you'll typically pick like under Visual C# Windows desktop application. Okay, you'll pick a location. For example, let me browse where I want to store the project. Okay, so if I go to, let's say, D drive, let me just pick a temp folder for right now. Okay, so I'm just creating some project. Let me call it test OpenCV. Or test CB, something like this, computer vision. Okay, so I gave the name of the project test UCV, Windows Forms application, Windows desktop. Click OK. Okay, so now, like I said, first thing we need is we need the library, the OpenCV library, so that we can do canny edge detection or anything other sophisticated things. Okay, so these days, anytime we have to download a library, okay, we use NuGet. Okay, so NuGet is the standard technique for downloading, doesn't matter, it's computer vision, it's deep learning, any kind of library. If you're using C#, you'll use this NuGet system, right? And NuGet is extremely easy. Okay, so what you will do is you will go to the project, go to the tools menu, and you'll see there's a NuGet package manager option, and then manage NuGet packages for the solution. So you will select manage NuGet packages for the solution. Okay, once you are here, then the default is it will come to the install tab, but click to the browse tab, make sure you're connected to the internet. Okay, then just search for whatever library you are interested in. Like I said, the OpenCV wrapper for C# is called EMGUCB as an example, right? So you will just type in EMGUCB. So it will search the internet. Okay. Oops. Okay, then hopefully we'll come back with emgu.cb. And you'll see it says .NET wrapper to the OpenCV image processing library. So anyway, all you do is select it. Okay, then just over here, select a project. and click on install, and this OpenCV will get installed in your project, right? So then once it's installed, then how do we load an image? How do we apply canny edge detection or other advanced features to it? I'll give you the tutorial, but whatever code I give you, this is the additional part you will need to bring the OpenCV library before you can play with it, right? Okay, so let me see if I have any already. So I'm looking for some small example with OpenCV I can quickly show you. Okay, anyway, it may take a little bit for me to search, so I'll put that handout with few simple examples, how to use the library and so on. Okay, let me just go 5-10 more minutes and give you one important concept today, and which is the canny edge detection, right? So if we go to kiwi.bridgeport.edu, okay, if you go to the handouts, one of the handouts over here you will see is canny edge detection. Okay, so I'll just quickly go through it so that you understand how this algorithm works. So anyway, there's an article by somebody which I thought is pretty easy to follow. Okay, so you guys should read this particular article. So anyway, canny edge detection has a few steps. Actually, let me show you what are the steps. Okay, let's go over to these steps. Okay. Okay, so the first step, as you can see, is to do low-pass filtering, which they call smoothing over here. So can you guys, if you were to do this, what kind of kernel would you pick over here to apply to the image to remove noise? I mean, average filter works, but what is a more, slightly better filter for that? Gaussian. So the typical choice is to apply a Gaussian filter in the beginning, right? Then finding gradients. So these are basically first derivative gradients. So what kind of kernel will you apply over here? The minus 1, minus 2, minus 1, 0, 0, 0, 1, 2, 1, right? And very similarly, minus 1, minus 2, minus 1, 0, 0, 0, 1, 2, 1. What is this called? What's a popular name for these two kernels?
Gradient filters.
Gradient, but with these particular values, it's called the Sobel filter. So this will be basically Sobel filter. Okay. Then there's a part called non-maximal suppression. Okay. The non-maximal suppression, very briefly, let's say we have some values. Let's say 45, 89, 73. Okay. Let me go one more over here. Let's say 60, right? And let's pretend for these set of values, we wanted to do non-maximal suppression. Okay? So basically, all that means is if the value is not maximum, zeroed out. So which one will be zeroed out? What's the maximum of these values? 89. So what does that mean? Everything which is non-maximum, make it 0. Make it 0. Make it 0. So the only thing that will be left out will be 89. So why do they do non-maximal suppression? Suppose here's some kind of image we have, right? And what we want to do is we want to keep the edges. We want to zero out everything else. So the gradient, would it be a small value on the edges or will it be a high value on the edges? High value. So if after finding the gradient, then if we did a non-maximal suppression, what will happen? Everything else will turn to black. 0 is the black pixel, right? And the edge will show up if we were doing, for example, the x direction derivative, right? Okay, so that's the purpose. Double thresholding and edge tracking by hysteresis, I'll describe in a second. Okay, but anyway, let me further go over here. So let's go to the first step, which was smoothing. What does this look like?
Gaussian.
Gaussian. Okay, so is it a 3x3 Gaussian or a 5x5 Gaussian? 5x5. And see, the numbers will depend on the sigma value. I forgot what sigma they used, whether they said over here. Sigma of 1.4. Okay, that's a popular choice to remove the noise, meaning do low pass filtering, right? Noise also appears usually at high frequencies. Okay, so that will end up removing the noise. So that's the first step. So I don't know if you can see it on if I directly take a look, it's a little bit better. But this is a little bit blurry image of this one after it has been passed through a Gaussian. Okay, now let's go to the gradients. Okay, what kind of filter are they applying over here? Sobel filter. This is the kernel in the x direction, kernel in the y direction, right? Okay, so this will end up enhancing the edges. And what is this equation for?
The gradient.
The gradient. Okay. Okay, so in addition to computing the gradient, so see, this is the magnitude of the gradient. Okay, they also evaluate the individual absolute values so that we can also find out the direction of the gradient. So direction of the gradient, as you will see, will be tan inverse gy over gx. Right? So anyway, over here, tan inverse gy over gx. Okay, why do we need the angle of the gradient? You will get the motivation in a second. Okay, so anyway, do you see the edges are being enhanced? So these are the gradient magnitudes over here, correct? Okay, now let's go to, okay, the angle part is coming in a second. Okay, now let's go to the non-maximal suppression. Okay, so first thing we do is, remember we computed the angle. Okay, so at every pixel point, okay, we are computing the gradient, meaning derivative in the x direction, derivative in the y direction, square it, take the square root. We also are computing the angle. Okay, remember angle was right? So suppose the angle comes out to be excuse me. Let's say the angle comes out to be 29 degrees. Okay? Or let me make it easier. 39 degrees. Okay? So if you take a look at this part, it says round the gradient to the nearest 45 degrees. So we'll treat this as 45, right? Very similarly, if the angle comes out to be 78 degrees, for example, this will be rounded to 90 degrees. So all gradients, as you can see, can have basically these directions over here. So there could be 9 directions for the gradients. Okay, so Okay, so if we go further. So let's say at some point in time, okay, these are the gradient directions, these arrows. So as you can see, this is 45 degrees, 90, 90, 90, and so on, right? Okay, and the numbers that you see over here, 2, 3, 5, 4, 6, those are the magnitudes of the gradient. So arrow is the angle, the number is the magnitude. So then basically what we do is, we do non-maximal suppression. Okay, in the direction of the gradient. Okay, so for example, take a look at this part over here as an example. Okay, all the gradients are in the vertical direction. So which is the maximum of 5, 7, 4, and 3? 7. So what will happen to these? So this will be zeroed out, zeroed out, zeroed out. So the pixel value will be zeroed out. This will be maintained. Okay. So very similarly, if you go to this same example over here, you'll see 6 will be maintained. Everything else will be zeroed. 5 will be maintained, everything will be zeroed, 6 will be maintained, 7 will be maintained. So basically, as you can see, the edge being created is something like this. Okay, so that's the purpose of the non-maximal suppression, to tell us wherever the highest magnitude is, because obviously that's the edge, and then further along the edges, see if we came up with a simple formula. Let's say if we came up with a formula, greater than 5, keep the pixel, meaning it's an edge. Okay, then the problem is, then, this will also become 1, right? Do I have another one? Another 5. This will become like, see, at a given point in time, regardless it's the x direction or the y direction, there can only be a single point on the edge, not 2 points on the edge, right? Would you see like a table's edge, then further like there's also an edge over here? No. So that's the idea behind non-maximal suppression in the direction of the gradient, so that we keep a single point.
So why is there no pixel that were kept for the 45 degree gradient?
In this example, no, but there could be an example like this, where let's say the direction is like this. So then basically what we do is we compare these 3 values to see which one should we keep. Whatever is the maximum of these 3, let's say this is 81, this is 50, this is 60. So then we'll keep this, and this will zero out. Right? Okay, so anyway. So that was the idea behind computing the direction and taking, okay, last point in this algorithm. So here's the example. So this was after we applied the Sobel. Then further, we apply non-maximal suppression. So then, as you can see, some of the inside is basically disappearing. Okay, so only the boundaries are getting right. So this is getting enhanced over here. Okay, last step in this algorithm is called the hysteresis step. So if I go back. Okay, sorry, there's one more step before this, double thresholding, and then which is tied to the hysteresis, edge tracking by hysteresis. Okay, so let me explain the idea of the double thresholding. Okay, so let's say we did the non-maximal suppression. We came up with some numbers, 40, 70, 80, 60, let me put one more value over here. Okay, just to explain, let's say 90. Okay, so anyway, let's say there's some other values over here. 60, 30, 50, something like this, right? So there's some gap over here, some gap over here. Okay, so in the double threshold thing, we pick a minimum value and a maximum value for the gradient. Okay, so suppose we said minimum should be 60, maximum should be 80. Okay, so then we have a concept of what is called a strong edge. So strong edge is in this algorithm is defined as any gradient that is greater than max value. Okay, so what was our max over here? 80, right? So let me put one more over here. Let's make it 195. Okay, so basically as soon as we apply the double thresholding, anything above 80 will be marked as a strong edge, strong edge, strong edge, right? Anything between 60 to 80, this will be called the weak edge. Okay, so this 60, let me put it like a dashed line. 80, okay, let's mark it as strong because it's 80 or higher. Let's pretend this way. This will be weak. What about 40? 40 is below the minimum, so we'll X it out. 50 is below the minimum, this will be a weak edge, correct? So let's pretend between min and max, or I can even make it 70 over here. Okay, so now we mark strong pixels or strong edge points and weak edge points, right? So the hysteresis step is pretty easy. Okay, here what we do is, the idea is keep the pixel or keep the gradient. The gradient actually is the value at a particular pixel point, right? If it is either a strong edge or connected to a strong pixel. Okay, so for example, okay, 9500 will treat them to be edge pixels, right? Now let's go to 60. In the neighborhood of 60, is there a strong pixel? Right? So we'll also keep this. We go to 80. 80 is a strong one, right? What about 70?